Here we go. Here we go. Overview of machine learning. So what is this machine learning thing? It's the way of the future. It's how all computers are going to work. I don't know, blah, blah. But if you ask a bunch of different people, you get a bunch of different answers. And I'm going to give you 3 answers right here on this slide. The first is that something that you might find on the internet. Machine learning is a branch of artificial intelligence based on the idea that systems can learn from data, identify patterns, and make decisions with minimal human intervention. Okay, so let's just parse that again. It's artificial intelligence, so sometimes AI and machine learning get a little bit confounded when you talk to people. And the idea is that the system takes data, finds the patterns of what's going on inside of the data, and then uses those patterns to make decisions. And then there's this minimal human intervention because machine learning really still is a field, and humans need to spend their entire energy trying to help computers learn even very simple things. I mean, still, that's a state of the art today. So that's one definition. Now, another more formal definition to let you know a little bit of what you're going to get into with this Mitchell book, one of the textbooks that we have in this course. So a computer program that can learn from experience E with respect to some tasks T and performance measure P. And so now P is the formal way of saying, well, how do I know I did well at the task or not? Did I get a high score? Did I achieve the goal? Did I succeed or fail? And there are lots of ways to talk about how to tell a machine learning system if it's doing a good job at a task, and we're going to talk about them a lot. So experience E, tasks T, and performance P, so that this program's performance at tasks in T, as measured by P, the performance measurement, improves with experience E, or getting more training data. So that's a little bit more formal way to say it. If we want to get a little more colloquial and conceptual, traditional computer programming works a little bit like this. So you have your computer and you create a program. And the purpose of the program is generally to take some input data and process on the input data and output something interesting. So like if you're going to do a mailing list processor, maybe you write a program that takes in a bunch of mailing list and processes it to clean it up and make sure all the addresses are valid, and then outputs the valid addresses. So that's a type of thing you might do with traditional programming. But what if you wanted to do it with machine learning? So machine learning still will take the data as input, and that would be like the mailing list in this very simple example, but it does a little switcheroni. And in machine learning, you input the data and the output that you'd like a program to produce for that data. Then the computer does some processing and does its machine learning, and the machine learning then outputs the program that you would then take up here when you were doing this in practice, when you were actually trying to process the mailing list. So you would give it the output that you'd like for the data. You would do the machine learning, and machine learning would produce a program. Then you could use that program with future instances of data to produce the output that you'd like, for, okay, I got to send out this week's mailing. How should I process it? So there's 3 ways to think about what machine learning is, and let's keep going. Now you could say, well, why do that? It just looks like you're adding an extra step of conceptual confusion to something where, like, hey, we know how to write programs. Processing mailing lists, not that hard. Let's just go write all the programs we need and not worry about it. Well, here's some situations where machine learning has really been an enabler. And the first example of this is what I like to call big problems. So imagine you have to take every song ever written and somehow categorize it. That are similarly with books and web pages. And, I pulled these numbers by doing a little bit of internet searching in 2019. And so maybe they're wrong, maybe they're right, but it gives you a sense of the scale of it. And there are just many, many, many big problems that the internet age has enabled. And it's not practical to use human effort to come up with all the corner cases and to create the program that's going to effectively process all the songs, books, web pages, whatever it is, social network posts, whatever it is that you want to process. So when you have a lot more data than a human can reasonably attack in their lifetime or in the amount of time that your startup has money before it's going to go bankrupt, well, then machine learning might be a good approach for you. But, and this is maybe a little bit of a subtle point, is that most problems aren't just big, they're actually open-ended. And what I mean by that is that, let's say you solve today's instance of the problem, you just wait another week and you have another gigantic problem to solve of all the new stuff that's happened since the last time you solved the problem. So when you have very large problems, when they continue to get bigger and bigger and bigger over time, machine learning is a very good approach to use. But the world is always changing. This is a little like sample stock ticker thing, like let's say you were learning a model to predict stock prices and you learned a model on this data and then you have this gigantic spike and crash. Well, whatever you learned here, or whatever program you wrote to deal with that version of this stock prediction problem is probably not going to function very well there. And you could see if you could look through here and see that really there's no very highly stable series of days or weeks or months or whatever this is, where you could imagine that, hey, I've got the program that's going to work on this problem. I can run it for a long time. So instead, what you might want to do is figure out how to get machine learning to learn a new program for what should I do in this situation? What should I do in this situation? What should I do in this situation? That way, you could always learn a fresh program and predict the very next day's predict whatever predictions you need to make for the very next day. And in that sense, by using machine learning, you're able to keep up to date with time-changing problems much more efficiently than you could if you were working with traditional, hire a human to constantly be updating whatever the program is that you're using to make these decisions. And then the final fundamental reason to use machine learning is intrinsically hard problems. And these are things that, are just a little bit too complicated for humans to figure out how to write the program. And often they'll come down to topics like human level perception, where a human's brain isn't quite capable to write a meta program to understand what a human's brain can do. Sometimes using machine learning with a lot of data can get you a lot further. For example, the first speech recognition programs were created in 1952. Right now you can talk to your watch or your phone or all these devices scattered around your house. And if you're very kind of clearly articulate what you're trying to say, you're pretty much expected to understand what you tell it to do and to do it. But this is because of machine learning attacking a problem that humans have been trying to solve for decades and decades and decades. And it's only more recently with machine learning type of techniques that we're able to crack through the very fundamentally difficult thing of doing human level perception. And there's other examples that we'll get to throughout the course, like computer vision is another case where doing machine learning has just recently really started to enable things that would never really have been possible doing a more traditional programming approach. Another reason to use machine learning in intrinsically hard problems is complex, open-ended games or interacting with complicated environments. If you think about the chess stuff, the first chess program was written in 1957. I guess, I don't know, I found this stuff on the internet. It's probably true. I might have missed something, and those chess programs are okay. They're okay. They play. And it took humans something like 40 years to beat Garry Kasparov with a computer. And I seem to remember that Deep Blue was not a heavily machine learning based approach. It was very much a search based approach. And so, 40 years of human effort to get something to beat a human master. And you'll see later in the course when we talk about reinforcement learning that Google's AI is able to learn using machine learning from scratch, zero knowledge, in less than 24 hours, a program that crushes Deep Blue, would beat Blue 1,000 out of 1,000 times, something like that. And so those techniques enable us to attack harder and harder problems and do more and more interesting things. And, in some situations like this, and chess is, I say, complex open-ended game. Chess isn't really that complicated. And so, as we want to extend computers and our ability to process and interact with much more intricate systems, machine learning is going to be a really important enabling technology. Okay, so now that's sort of why to use machine learning. And let me just go through and level set with some examples of how machine learning has been successful over the last decade or something like this. And I would say maybe if I was giving this course 10 years ago, I'd spend a lot more time on this slide trying to explain these things. But I think you all probably are familiar with these, but just a quick level set here. one big success of machine learning has been the human's ability to access the knowledge we need just at the touch of a button. I mean, I don't know, like I remember when I was a kid doing a research project and going to a library and looking through the card catalog by hand and then going to an encyclopedia and opening it to the right. Man, it could take forever just to get a simple darn fact. And now you can just go to one of these web searches and type in your question in plain language. You don't even need to like think of what's the right keyword. You just type what you want to know. And more often than not, the answer will pop up right there in front of you in a nicely formatted, either a nice web page or even extracted information from web pages into really clear answers. And we're going to see later on in this course, when I talk about the one of the design patterns for machine learning, how something like that is structured and all the places in a system like that are really enabled by machine learning. I'll just say that machine learning has been a real enabler for humans organizing and accessing knowledge and has made a lot of people a lot smarter. Another place where machine learning is used heavily is in finance. And you know that this is true because Pedro Domingos, who used to teach this course, no longer, maybe he's going to come back to the university. I don't know. I haven't talked to him in a while, but he's off doing finance. And the idea is that like algorithmic trading, like should I buy this stock or sell this stock? Is the stock over or under priced? That's a prediction problem. You can look at features of the stock, the history of the stock, how it's been trending, and decide, I think the probability the stock will be higher tomorrow is 75%, something like that. Loan underwriting is another very clear example of machine learning, is like look at the credit history of a particular person, look at the loan amount, and predict the probability that that person would default if we gave them that loan. So you can use computers to create very detailed models, very accurate models of the risk of doing credit things and use those to run businesses. Portfolio management, I guess it's a little bit like algorithmic trading, but you might look at how should we go between industries rather than looking at specific stocks. You might look at industries or higher level things and combine that with forecasting. I've heard of all sorts of interesting machine learning in terms of like, what is the corn crop looking like this year? Well, I don't know, but let's get some satellite images or fly some airplanes and have them take pictures of fields and then use computer vision to decide if, hey, that field looks like it's going to have a high yield or a low yield. I've heard of things like even sales, looking at images of parking lots at the mall in the first few days of the Christmas season. People might try to predict, well, how much traffic are malls getting? Is that better or worse than last year? Should we, do we think we're going to have a good year or a bad year, or what do we think is going to happen? So there are all sorts of applications in finance. Another big area of success has been marketing and e-commerce. And, just the easiest way to see that this is true is look in your inbox, particularly your Hotmail inbox, and you're going to see all sorts of marketing and e-commerce. And I just tease because I did used to work on Hotmail's anti-spam system, and I don't know. I mean, when I was working on it, it was perfect. Everything was solved. I think things have gone, I don't know. I'm just teasing. But there are also some good sides to marketing and e-commerce. For example, personalization. Why is personalization such a good thing? Let's say I go to a web page. Everything's a mixed bag and you could say it's good and bad. But if I go to a web page and I see an ad, I'd prefer to see an ad for something that I'm interested in. It's got to be there. There's got to be an ad there. But why would it be something irritating to me? As just like a person, I'd rather see things that I like to see. And you can look at, news sites and other things like that in terms of like showing me the news that I want to see. Targeting is maybe a little bit more on the spam side, which is as a person who is going to spend money on marketing, I want to know who to spend that money marketing to. And so that's sometimes called targeting, and you can think of it as like conversion prediction. And the idea is you would look at the properties of the product, you would look at the properties of various people, and you would say, well, which of those people has a probability of responding to that ad greater than 3%, 5%, something like that? What is the conversion rate we would expect a particular person to have for that product? And then you would focus your money in the places where it's most likely to give you the best return. Predicting churn is about looking at customers. Like, for example, if you're running a gigantic productivity suite, you might want to look at, well, how are my customers, my important like business customers, interacting with the product? And which customers seem to be losing engagement with the product? Which customers do I think might switch to a competitor? Should I consider building features specifically for that customer, or perhaps like talking to my sales team to try to work out some sort of a contract with that customer that would put me in a better position going forward. And then recommendations, like what song would I like, Netflix, which movies would you like to see, all sorts of based on the properties of you and what you've been doing recently, here's what we think you'd like to see next. Another important area is abuse and security. So like I made that little joke, on the marketing and e-commerce. Now you want to say, well, how do I stop that stuff from getting at users, particularly when it's bad, like spam? There's more malicious things like I want to try to take over your computer. So you might talk about things like anomaly detection, building machine learning based models to look at how's a computer or a typical computer behaving over a long period of time. And can I predict, is this computer behaving like a typical computer, or is it behaving in an abnormal way where I might like to either, for example, request additional information from that computer so I could identify a new type of attack, or maybe somehow quarantine that computer so it can't spread an attack or can't access information quite as well as it used to. So a machine learning, in this space would be like, let's look at a entity, predict the probability that it's behaving well. If it's behaving well, give it access. If it's not behaving well, restrict its access. And machine learning is a very important part of abuse and security. Robotics. And to me, the favorite robot that I own is my car. It's my Tesla. A few years ago, I just realized, my commute is the worst thing in my life. So I went and bought a Tesla, and I didn't really regret it. Even now in the apocalypse, when I don't have to commute, I still love having the Tesla. It's like I drive by other car dealers and I look over and I see all those shiny cars lined up and I want to yell out the window, hey dude, Fred Flintstone called and he wants his piece of junk dinosaur car back. Nothing is like what machine learning has enabled in a car like a Tesla. There's, and I don't know all the details, but there's dozens of deep neural network human level perception models running in a Tesla car at any time, and that information is being synthesized, and there's this thing called localization, which what that means is a robot understanding where in the world is it right now. I mean, you can use GPS, but you can also do it by looking around and figuring out what are the things that I see around me and how have I been moving recently. And then there's the control systems, like when do I steer, which way, this or that. And perception, I just talked about perception. And then this little robot that is kind of pencil sketched behind there, this Boston Dynamics thing. Those things are so cool, man. They walk upstairs and they bounce and they jump and you can shove them and they don't fall over. Human level perception and that kind of control systems are benefiting from the types of techniques that we're going to be talking about in this course. The other one is digital assistance. Connect is something I've worked on personally. Siri, I don't want to talk too much or they're all going to start responding to me. Was she going to? Okay, she didn't hear it. We're safe. But, just the sheer number of machine learning based systems that get integrated by these is incredible. When I speak, I just say some natural sentence and it needs to decide, should I do a web search? Should I launch an app? Should I respond with some information? They're very, very incredible things. The other one I did mention was games. StarCraft and Go recently, and those are highly complicated compared to at least chess. Open-ended games and machine learning-based techniques are starting to crush humans at them in actually, pretty surprisingly short amount of time from going from scratch to beating a human, like the world-class best human in the world at the particular game. It's very interesting. And then, which way do I have to lean here? I gotta lean. There's all this other stuff, many other, like healthcare, doing diagnoses, social networks, all the interactions, which tweet should I show to who, conservation, like can I predict weather patterns, and can I predict all sorts of crazy stuff, translation, you can pick up an app and speak in one language and it speaks out the other side in another language. This is just a sampling and I could have probably gone on and on. It's not really that important to what we're doing here in the course, except to say that most important whatever. I'm a machine learning guy, but very, very many important applications in the world, things that humans care a lot about, machine learning is getting into them and is making them better and is allowing us to interact with systems and with each other in ways that, 20, 30 years ago, we wouldn't have even really dreamed of. So it's an exciting time to be part of machine learning. Okay, so I've given a lot of rah-rah, but machine learning isn't right for everything. And let me tell you a little story here. I think I mentioned in the introduction that sometimes I tease program managers, and it's because I was a program manager for a little while. I really like program managers because I like to tease them. No, because that's not, but But so here's something that actually happened to me, and I feel like it's happened to me multiple times, and maybe it's just because I'm so on edge for it. So I'm sitting in my office, and some program manager calls a meeting with me, and they come in and they start explaining this architecture diagram right here, this crazy thing, and they're talking about SQL backends and cloud storage service and message passing and all sorts of crazy stuff, and like I'm sitting there saying like, what you're talking about, this doesn't make any sense. That'll never work that way. I'm not really like into that sort of engineering. I'm a machine learning guy, but it sounds like what you're talking is crazy and it could never possibly work. And I'm just about to say something, and then it starts to dawn on me. I'm like, oh no, I know why this guy's here. I know why he's talking to me. This is going to be terrible. And sure enough, they go like this. And then we have machine learning, and machine learning's right here. And somehow in their mind, machine learning is the magic pixie dust that's going to take all that gobbledygook and turn it into a working system, and I'm the person who's going to do it for them. And then, sometimes they get mad when I say, no, it doesn't work that way. We can't do it. They're like, what's wrong with you? Why won't you do machine learning for me? Why? You're just a hard person to work with because you won't do my machine learning for me. And I'm like, no. So like when I talked about in the intro lecture, we got the 3 parts that this course is like, the algorithms and the concepts, how to do professional level modeling. And then the third one is like, where in a system do you put machine learning, and how do you have to structure the system and the machine learning so that they support each other? And it's not just some gobbledygook with somebody sprinkling pixie dust onto it saying machine learning is going to make this obviously broken system work. So what are some ways to realize that you're bumping into this sort of situation? Like I said, when machine learning is not set up for success, like you're trying to get it to do too much, or you don't have the right training data available, or it's not able to change the user experience the way it would need to actually have the impact that you want it to have. So when it's not set up for success, machine learning can be a very expensive way to fail. Another place is simple problems. Like let's say you want to do a program to calculate a balance update when somebody does a withdrawal from a bank. So you have balance before, withdrawal amount, balance after. Those are all the components that I talked about on the other slide. You got the data, you got the output, you want to learn the program. You could do it. You could try to do machine learning to learn how math works. But really, that's such a simple thing to do. And machine learning is not really set up to be 100% accurate all the time. And so if you're trying to go after simple problems with machine learning, you're almost certainly doing the wrong thing. And I'll tell you why this is really an insidious problem. It's because machine learning is so hot that everyone wants to be involved in machine learning. And so you can find people who will come along and say, hey, I had this really simple problem and I got out an elephant gun and killed it with machine learning. Like, no, dude, write a program. That's not a good place for machine learning. So got to keep your eyes out for like problems that don't need machine learning, that people are trying to jam machine learning down its throat. And this is, deterministic problems where the answer is very clear, like that banking case, and problems that are efficiently solved other ways, like if you can hire a few people to hand label a few things, or if you can get your users to give you the feedback that you need, maybe you don't need to make a prediction. We'll go through other examples of other ways to solve problems as this goes on. And a place you can look for more information, like to better understand really what is the cost of machine learning, is this very neat paper, Machine Learning, the High Interest Credit Card of Technical Debt. It's a catchy name, and it's really a great way to think about it because machine learning comes with all sorts of new problems that software engineers and the abstractions that you'd think of don't naturally address. And if you use machine learning without really considering how it interacts with systems and how its life cycle is different from a traditional piece of software, you're going to get yourself into a lot of trouble and get yourself wedged so you can't change your system anymore. We'll go through a lot of this type of stuff throughout the course. So we've been through a little overview of machine learning and some ideas of when it's good and when it's not good and what some of its successes have been. Now we're going to try to walk ourselves towards our first machine learning and really get a sense of what is it. And at machine learning's core is data. When you look at data, you could think of 2 things. There's unstructured data, like just raw bytes, or data that was packaged for some other purpose, like the raw contents of your hard drive. I'm sure there's a binary on there that's designed to be loaded by your operating system and run. That's data, but it's very unstructured, or it's structured according to something that is not relevant to machine learning. In machine learning, we talk about using structured data in general. And this is like, if you know SQL and relational databases, this is pretty much similar things. And that is, instead of having a collection of books, each book is represented by certain structured pieces of data. A structured piece of data might be numerical in that it's a number. It might be categorical in that it's a value from a small set of possible values. For example, if you were talking about a collection of ebooks, the category might be its genre. So the categorical data for a particular ebook might be it's either a romance or it's a sci-fi or it's a thriller or whatever it is. You can also have binary data, which is a 0-1 field. We'll see an example of this quite soon. Like, is the web page on a US server or is it on a foreign server? That might be a binary piece of data about a web page. Structured data can also contain text fields in that, like, here's the title of the book, or here's the first chapter, or here's all the text of the entire book. But, text that is somehow semantically described as a particular cohesive piece of text. Structured data can also have relationships, for example, pointing from a web page to the other web pages that it talks to. But the point of this is that to do machine learning, you have to start with unstructured data and take it and through some process create structured data. And that structured data, we'll see in a few slides, is machine learning algorithms have been developed that know how to deal with all of these different types of structures and can work with them and produce programs that know how to process them. So a particular example that we're going to walk through here is, let's talk about ebooks. And here is a structured table representing your collection of ebooks. So in this table, there is one row per book. And on each book, you have a text, structured text, which is the title of the book. You have a numerical feature, which is the number of pages in the book. You have another numerical feature, which is the year the book was published. You have a categorical feature, which is the genre of the book. You have a binary feature, which is a 0-1 if the book was a bestseller. Then you have another binary feature, which is kind of a silly feature, but just to illustrate, you could look at the text and convert it into a binary feature of, does the text contain the word robot anywhere? I don't know why you do it. It's something you could do. And then you have a relational feature, which is the author ID, which would presumably go off to some other table, which talks about properties of the authors of the various books in your data set. And so this could be like a link to there, or reference to there, or reference to there, something along those lines. So here's an example of you've taken some books that could have like 100,000 words in a novel, something in that ballpark, and you've converted each book into this structured row, which contains salient information that you think might be helpful with the machine learning task that you're going to do. Maybe or maybe not. All right, so now we have the structured data, but machine learning doesn't take that directly as input, because remember in machine learning, you had this notion of here is the computer and you're going to input the data and the output that you want to see, and that it's then going to output the program. So that's what we need to get to. And so we say, well, which part of this table do we put into that data arrow? Which part of this table do we put into that output arrow? And the program is something we'll talk about later. And the way to answer that is like, let's say, it depends on what you're trying to predict. So let's say you're trying to predict if a book is a bestseller or not. Well, if that's your prediction task, then the input to this data arrow would be what we would call features, or sometimes we would call it X. Those are sort of synonyms. And it is every column that is not what you're trying to predict, that you think would be useful to predict the thing that you're trying to predict. In this case, you could take the book title, you could take the number of pages, you could take the year published, you could take the genre, you could take whether or not it has the word robot, you can take information from the author table and pull those features in as well. You could pull in all sorts of other crazy stuff. That becomes the data. And now let me say that again, sometimes this is called the features of your machine learning. Sometimes it's called X, which is like the vector of input features. Each column here is a feature. X is the vector of all of those features. And, like each row is a training sample. So those are some definitions that you might say. Then you would take that bestseller column and that becomes what you're trying to predict, or the output arrow in that little diagram I drew at the top there. So the output you're trying to predict is this binary thing, which is 1 if the book was a bestseller and 0 if the book was not a bestseller. Now, some synonyms for what this is called is you could call this target that you're trying to predict, you could call them labels. Sometimes they're called f of x, sometimes they're called y, because because y equals f of x, so the job of machine learning is to come up with a function that can take this as input and produce that as output with high accuracy. Little bit of lag there. Okay, so now we're going to talk about one type of learning and give another version of an example of what I just drew you on the last slide to just show you how this stuff progresses. And that is supervised learning. Don't worry, I'll talk about what that means and what the options are for learning in a slide or two. The idea of supervised learning is that you're going to have a machine learning algorithm. You're going to input the features or the x's into the machine learning algorithm. You're also going to input the labels or the y's. These are the synonyms that I'm trying to just slowly beat into you as we go through this. And then the machine learning algorithm is going to output a program. And here's an example of what that program might look like, although it would never look like that. But it says define function f. And function f takes as input one variable for each column over here. And it returns 1 if the book is a bestseller and 0 if the book is not a bestseller. So it returns, the same type as what those labels were. And that, at a high level, is what a simple supervised machine learning algorithm would do. If the y is discrete, that is, if it has a small number of possible values, then you would say that you're not just doing supervised learning, you're doing classification. If y is continuous, that is, instead of predicting the number of pages in the book, instead of trying to predict a 0, 1, or a binary thing, then you would say that it's a regression, because these are just some vocabularies that you are going to need to learn. I'll use them again and again. You're going to pick this stuff up. This is just the first exposition, so I'm giving it to you a little bit slowly. Then if what you're trying to do is to predict the probability of something, you would just call that a probability estimation, because la-di-da. But so you might say, instead of saying this book was a bestseller, you might want to be able to say this book is 75% likely to be a bestseller. And that would be an example of doing probability estimation instead of doing classification, something along those lines. Or regression, you might say, how much money is a book with these properties going to earn? And you try to do a regression and say, that's going to earn $14 million or something along those lines. But that, this same pattern works for classification, regression, or probability estimation. It just is a function of which of these columns do you take and use as your labels? If you used year published instead of bestseller, you'd be doing regression instead of doing classification. So that's an overview of what a simple kind of the structure of a machine learning algorithm would look like. This is where you guys know you're lucky that I'm recording this instead of doing this live, because man, I went through this slide once. I rambled everywhere. It was terrible. It was crazy. So I'm going to do it again. I'm going to be a little more focused. I'm going to tell you what you need to know. All right. So here's an example of how happy you are that I'm not doing this live, because I've done this slide 3 times now. This will be 4. And every time I do it, I'm like, blah, 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 blah. I got just, this machine learning stuff is so exciting and I want to tell you so much, but I just have to restrain myself and be focused. So here we go. We're going to be focused on this. And what I want to talk about here is that there are many, many, many machine learning algorithms, thousands. I, getting my PhD, came up with 6 or 7. PhD researchers all over the world are currently creating dozens more, and they have to create them or they won't get their PhD. So there's a lot of learning algorithms, and it's nice to have some structure to understand, well, what is that learning algorithm like? What are its kind of fundamental properties? And you might say that there are 4 important fundamental branches of machine learning. And those are supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. So supervised learning we talked about on the previous slide. And there the notion is that you have the X and you have the Y. Or as we've said, some of the synonyms, we have the features and the labels. Or we have the X and we have the F of X. And supervised machine learning algorithms are able to work with data of that format to produce the type of programs that we've talked about and we'll see many, many times in the future. And I'd say supervised learning is maybe by far the most commonly professionally used type of machine learning, although, maybe that's just me and my experience, and other people might pick something else here. Unsupervised learning is a type of learning where you only have the X and you don't have the Y. And what would this be? You might come to some new data set and not really know what you're looking for in it, or not really know how to make progress, but you'd like to be able to ask a machine learning algorithm, hey, go find me the structure of this data. For example, if you're talking about customers on a website, an unsupervised learning algorithm might say, look, I don't really know what you're going for, but here's 10,000 customers that are all pretty darn similar. And it might find like 40 different clusters of very cohesive groups of customers that you could go do further analysis on, pay money to get some labels, like hand label some of them, and then start doing supervised learning. And that brings us to semi-supervised learning, because in practice, you almost always are somewhere in that process of going from, you're not really dealing with the raw data anymore, but you haven't got labels for everything that you might like to have labels for. So you're doing some combination of exploring the data, trying to find insights from it, and then using supervised learning algorithms to make progress. And there's actually algorithms for doing semi-supervised learning, and we're not going to talk about any of them in this course. Those are more like, the way we're going to talk about this topic in this course is more about the machine learning engineering issues and how to position machine learning in your system and deal with this semi-supervised problem external to the machine learning algorithm itself. Then the final category is reinforcement learning. And this has been the technology that's really enabled all the open-ended game stuff and the control systems and that type of, and robotics is a big, been really enabled by reinforcement learning. And here you don't have X and Y, you have an environment, and you have an agent that can interact with the environment, and then the environment tells the agent what happened. So reinforcement learning is about figuring out how to efficiently take an agent and kind of interact with an environment in the right way so that it can start to figure out how to do the types of things that you'd like that agent to do. And we will talk about a lot about some supervised learning. We'll have 1 or 2 lectures on unsupervised learning and 1 or 2 lectures on reinforcement learning in the course of this class. Now, each supervised, mostly supervised, but each supervised learning algorithm, which like I said is going to be the bulk of this class, has 3 major components. There's the model structure, and what the model structure is what does that program that it produces look like? So you could have a program that's a whole bunch of if statements, or you could have a program that takes all the variables and multiplies them by each other. You could have all sorts of crazy model structures, but any learning algorithm will produce a particular type of model structure. Okay, that's number 1, that's the model structure. The next thing that you're going to have is a loss function. And a loss function is like, remember when I talked about Mitchell's P, the performance evaluation measure? A loss function is an evaluation measure. And that is, you take the predictions that your model makes and the correct answers, and you apply the loss function, and that tells the machine learning algorithm, well, how good are you doing? So at any point in the machine learning process, the algorithm can stop and say, well, what's my current loss? How bad are my mistakes? Am I heading in the right direction? The third component is optimization. And that is, how do you create that model? What's your process for doing it? Are you doing some kind of like mathy thing where you're trying to do some fancy like integer programming optimization? Or are you doing a greedy search where you're just slightly making the model more complicated at each step and growing up a more and more complicated function? So when you're talking to someone, the first thing, you say, well, what type of algorithm is it? Oh, it's a supervised algorithm. Okay, well, what's the model structure? What's the loss function? What optimization does it use? Then you'll have a pretty good sense of where they're coming from and how interacting with that learning algorithm would be if you were trying to use it in practice. So now I'm going to go through each of these 3 things in a little bit more detail. Okay, so now let's talk about the model structure. And I'm going to introduce 2 pretty common model structures at a super high level. We're going to go through both of these in a lot of detail as the course progresses, but this will just be your first introduction to decision trees and logistic regression. So anyway, here we have the data where the features and the labels. I know it's confusing, but you're going to get bored of me saying it. But, if we were doing this class live, I'd know when you're bored of me saying it. Now I won't know. So I'm just going to keep saying it. I don't have any feedback. I don't have any signal. Features and models and features, labels and blah, 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 blah. I can talk forever. La-di-da. So now we have that. And now what if our model structure was a decision tree? Well, this is what a decision tree might look like. It's a function that, like, it takes in the x's like we talked about before. So each column is one of the input variables. And the way a decision tree works is that it does if tests on some of these features. And based on the values of the outcomes of those if tests, it will return one of the possible answers. So in this particular case, it says if the year published is greater than 1990, and if the genre is science fiction, then it's going to be a bestseller. That's all there is to it. That's a bestseller. If it's not a science fiction book published like after 1990, nobody likes anything except science fiction. So if it's not science fiction, it's not a bestseller. Otherwise, test the author and be like, hey, so if it was published before 1990, you test the author. And I mean, come on, you guys know how to read code. I don't need to like walk you through that. But here's the predictions that decision tree would make for this data set. And you would see that it gets that wrong, gets that wrong, gets that wrong, gets that right. Okay, so this decision tree basically is terrible. Don't use it, right? Like, and we're gonna get to more about what I say. Well, it's terrible. Don't use it. We're gonna get to many more layers of precision about what it's terrible means. One of them is, the accuracy. In this case, it's 25% accurate. And the other one is generalization, which is how well will it perform on data that we don't know about today. So for example, if a new book comes in with some new title, like the latest book I write, if this decision tree performs kind of on average as well on this new data as it did on this data that it was used to train on, that's a good sign. That means it's generalizing well, and that's a nice property that you want your machine learning models to have, is you want them to generalize. And I glossed on that a little bit. Don't struggle with that one. We're going to talk a heck of a lot about generalization. It's just like introducing that topic. Here's another form of model. We'll get out of the way a little bit, like something like this. And this is a linear model. And next lecture night, we're going to be talking about logistic regression, which is one way to learn a form of a linear model. The structure of a linear model is that it takes certain of the input features and multiplies them each by a constant. So it says the year published times 0.75 plus the number of pages times 0.5 plus the author ID times 0.1, which is actually a terrible thing to do. Never do that. It's just for an example. And then you would say, if the sum of all of that is greater than some threshold, predict 1, otherwise predict 0. So that's what a linear model is. It's a weight for each input feature and a threshold for prediction. So these are two different model structures, both heavily used, both being very successfully deployed in many places in the world. In this case, this guy got 1 right here, got 1 wrong, got 1. So this one was more accurate than the decision tree, but 50%, you might as well be flipping a coin. Terrible, don't use it, right? Here's other examples of model structures and linear models. We're going to talk about, that's our first learning algorithm, the first module of assignments. We're going to be implementing logistic regression and linear models. In the second set, we're going to do decision trees and ensembles of trees. Instance-based methods, we're going to have a lecture about that. We're not implementing them this year. Neural networks, that's module 3. We're going to spend a good amount of time implementing and working with neural networks. And then there's this whole kind of area of models called graphical models or probabilistic models, where you really try to learn the probability structure in your data directly rather than just trying to predict a particular column. You try to learn kind of the whole of what's going on. And those techniques can be very powerful, but they're maybe less used in practice. And we'll have several lectures about those, learn more about that. All right, like I said, 3 components. We just did the model structure. Now let's talk about the loss function. And in general, the loss function is like, okay, I've got this new model structure. did I make progress? How good is this new model structure? Should I keep it? Should I go back to the previous one? Am I heading in the right direction? Well, that's what a loss function will tell you. And in that example on the previous slide, we talked about the accuracy of those two model structures. Like the first was 25% accurate. I think the second was 50% accurate. And, that's simple. That's what you and I understand, but that's not what really people use for loss functions. And there's a couple of layers of why. One is that not all mistakes are the same. And you might want to reason about this or express this. Like precision and recall talks about false positives and false negatives, which, I'm not going to explain those to you on this slide. We're going to get into those in the very next lecture. But, you can make a mistake of saying something's there when it's not there, or saying something's not there when it is there. Those are very different. And you could talk about the cost of those different types of mistakes and say, hey, my loss function should incorporate the fact that when I say that there's someone at the front door, but there's not someone there, that's 10 times more irritating than the other type of mistake. Another common thing is something like squared error, where you could say, making a small mistake is okay, but making a big mistake is actually a lot worse than making a small mistake. And so you might want to encode that in the loss function that you use to decide which model structure is better or worse. There's this other thing of being smooth and continuous. Like if you want to take the derivative of something, which is some of this machine learning math that you need to do, you need to have certain properties. So accuracy, cost and utility, some of these things don't have, intuitively you would think like, just have my machine learning algorithm do that. Well, then you can't take the derivative, and then many of the optimization techniques we're going to talk about on the next slide just won't work for you. There's also probabilistic interpretation. Some people really like those and find them to be important. So you might talk about what is the probability of my data given the particular model, as instead of saying, well, what's the accuracy of my model on the data? Just say, well, what's the probability of that data given that model? Then there's, again, get my head in the way. Then there's this notion of like the complexity of the model structure might get out of hand. So you might want a loss function that tends to favor smaller models, even when larger models are more accurate on the training data. And there's going to be several lectures on that, and some terms that you can, overfitting is something where, you might want your loss function to incorporate some of those types of properties. And there's all sorts of proven useful things, entropy, KL divergence, on and on and on. Log loss, what's some other ones? Binary cross entropy, we could talk on and on and on and on and on about loss functions. And in the course of this course, we're going to use probably like 4 or 5 different loss functions that we're going to end up implementing. And the third part is the optimization. So now you kind of know the structure of the program you're creating, the model. You know the loss, which is how good is it, and now you want to find the right program to return for any particular training set, and that's the optimization process. So you can do greedy search, like try n changes, like start with a very simple model, randomly put n changes into it, calculate the loss for each of those, and repeat. Greedy search, there you go. You could do all sorts of other crazy stuff like gradient descent, which is start with your first model, calculate the gradient of the loss function, and use that gradient to make the update to your current model that most reduces the loss, and keep doing that until you converge. Linear programming is you might express it as a series of constraints and do a linear program that outputs what your model structure could be or should be, or like it meets all the constraints that you are trying to have or finding the optimal. Regularization is what I talked about also on the loss functions when you're controlling complexity. Well, you might also control complexity within the optimization to like limit the number of steps of gradient descent you take or something along those lines. By the time this course is done, you're gonna know when and why you might want to do something like that. And there's lots and lots of variations of optimization function. Okay, model structure, loss, optimization. There you go. Those are important components that are part of most machine learning, supervised machine learning algorithms. La-di-da. The next thing I want to talk about is let's look at a slightly more like, how does this work in practice? Like we have all these abstract components. Well, what would I need to do in order to use machine learning in a particular system? So maybe you have a process generating data, like this is a log source in your e-commerce store. And so every time somebody interacts with the e-commerce, clicks a site, views something, whatever, you get the properties of the product that they interacted with. And that is essentially an unstructured data source, which is like everything you have in your database about that product. Maybe it's already relational. not totally unstructured, but maybe there's some unstructured elements. You also get, through a little bit of time traveling, you can see like, hey, somebody interacted with that product, and then, within the next half hour, they bought it. So now you have the properties of the product and the label, which is that user is going to buy that product. Now we have a setup for machine learning that might be actually very valuable if you're running some sort of an e-commerce site. So the first thing you need to do is some feature engineering. So you take that X, which is written there as kind of like, this is the raw features, and you need to convert it into the features that you're going to use in your training data. And let's say, we'll talk about different feature engineering approaches, but let's say you convert all the properties of the product into just 4 binary variables. Like, is the thing contain yellow? Does the title have the word happy? I mean, whatever it is, who knows? We'll talk about how to get there. And then you have the Y, which is very trivially a binary variable of like, yeah, that guy's going to buy within a half hour or not. So there you go. You have a training example. You can create an entire training set of people interacting with your site for a day, a week, a month, whatever that you want to do. And you'll have just kind of a lot of data. If you have a large site, you could have really kind of an open-ended, very big, time-changing data set. Now we know how to get the data, where it comes from. We see like conceptually, yeah, I could see how to convert it into a training example, into a training set. Now let's talk through some of the processes of thinking of how would I make a machine learning algorithm and what types of things would it have to deal with to be successful. So if we take these 4 binary variables as input, we'd say our model structure is just any Boolean function on those 4 variables. We could say our loss function is accuracy of the prediction on the training data. And we could say that, like, let's start to think about like how we would search through that space to produce the best model. So anyway, a simple example of this is like f of x equals x1, where it would say, here's a simple thing that just predicts whatever x1 says. So it would predict 0, 0, 0, 1, 0, 1, 0. And if you kind of like eyeball this, like you'd see that that's not a very accurate model for this. It's something like half right. So let's try something more complicated. Maybe we do a little kind of random restart and pick something else. I would see x1 and x2. So this would predict 0, 0, 0, 0. Okay, only predict 1 there. Okay, that's terrible. Do not do that. And we could go on, and we could say, well, like, here's all the possible things we could do. And the reason that I'm saying this is these can get very complicated, and there are a lot of possibilities. And this is kind of one of the fundamental problems that you deal with in machine learning and thinking about how do you want to do this model search, is that even in this very simple constrained setting, there are 2 to the 2 to the n Boolean functions on n Boolean variables. So that means that there's 65,536 things that we could try. And if you think about it, looking at this data set of 7 samples, which one is right? You could say, like, conceptually over here in the process generating data, there is some function in the universe, in the world, that we're trying to recover. And, assuming we didn't mess up anything too bad in this process of going into what our training set looks like and what our features are, you might say, hey, one of these things is the right function. That's what we'd like to get back. But the problem is that our training set only has 7 samples here. And so you start to quickly bump into the fact that you could find this function, and we could set up some search process, and we find out that if we said f of x equals x4 and not x2, x4 and not x2, well, you can click through this, and I'm not going to do it real time, but you'd find out that that gets all 7 of these examples right. So are we done? I mean, is that like we've solved it? We have 100% accuracy. We have produced a model that predicts all of our training data correctly. Declare victory, we win. No, unfortunately not, because there are actually like a really large number of possible functions that get all of this training data right. And so the fundamental problem of machine learning is figuring out how to navigate this sort of like trade-off between wanting to build complicated models, not having enough data, and wanting to learn the model that actually is going to predict what's going on in the input data. And keep in mind that like we've already made a pretty strong assumption, which is to say we are only going to use Boolean functions. But as we've seen on the previous few slides, there's lots and lots of ways to represent models. So we could probably find hundreds of thousands of ways to properly classify these 7 samples using all sorts of models. In fact, I'd say like hundreds of infinite. There's an infinite number of models that we could come up with that properly classify those 7 samples. And so kind of the fundamental challenge of machine learning is finding the one, finding the several, finding A that works well on the training data that we have today, but will also work well as this process generating data proceeds into the future. We're going to talk a lot about those types of challenges and what you could do. Give another slide that talks through more of the things that could go wrong and why machine learning isn't really just a simple thing to do, but it requires a lot of work, a lot of skill, a lot of kind of like sticking with it to help computers help us. One thing that could go wrong is that, like we described on the last slide, we learn something that doesn't match the process. And then we would say that the model that we learn does not generalize to new data. So producing a model and testing how well do I think this model I have will generalize into the future is a fundamental skill that a modeler needs to do on a regular basis. Another thing that could go wrong is that you don't even collect the right data in the first place. Like I just said, oh, here's the properties of the product, but products could have a lot of properties. I mean, you could think of like not billion, but like thousands, tens of thousands of things to record about a product. And maybe you won't be able to log everything you'd like to log. Maybe you don't even have the right data in your representation to properly model the process that's going on. You know, you just don't have the information you need. So you're kind of like, busted out before you even begin. But maybe you do have the information you need, but now you have to do feature engineering, which is convert that raw data into the structured representation that your machine learning algorithm is going to take. And there's all sorts of ways you could mess this up and feature engineer incorrectly, so that you throw away the ability of your model to capture what you're trying to go after. Another thing that could go wrong is that your training set is too small or is actually explicitly biased. And too small and generalization are somehow related. Like the more data you have, the less likely you might be to learn something that happens to match all the data that you have, but doesn't generalize to the true underlying process. But there's also this problem that, this X your user will buy it. Maybe you say, well, I will say like Y equals 1 if the user buys it within 30 minutes. But there's some process in your system that doesn't calculate things correctly, or there's some reason that users often tend to put things in their shopping cart and come back later to complete the purchase. So you may be only capturing a small portion of what you're trying to go after because of the way logging works and your system works. Another problem is that you might pick the wrong type of model. And this could have a whole bunch of different ways to talk about picking the wrong type of model. One is that your model simply cannot represent the underlying process that's going on, and that's called bias. And the other is that your model is very kind of sensitive to the noise in the data and to the minor fluctuations, and that's called variance. And so in order to get a model that generalizes well, you have to understand each learning algorithm, how they behave in terms of bias and variance, and which is appropriate for your current setting. And I know that right now I'm going a little bit fast, and sometimes I like to do this. Is I like to talk the way machine learning people might talk around each other. And you will, don't worry about this today. Just take these words and start to soak into them. We're going to go through this in great detail. But let me give you an unfortunate kind of terminology thing. The word bias means a lot of things in the world today. And, there's the colloquial, the popular definition of bias, but there's kind of technical definitions of bias, and they overlap, and it's unfortunate. So you could say my model is biased in that it tends to make mistakes for particular types of users. That's bad. That's not what I mean by what's on the slide here. You could say a model is biased because it is unable to represent the concept I'm trying to represent, or the underlying concept in the data. And that's another type of bias, that it's just the model is simply unable to represent it. And you could say that your data is biased because the process that produced the data somehow led certain labels or certain features or certain products to be overrepresented or underrepresented. And, to some degree, they relate to each other. And we'll talk a lot about this type of bias. We'll talk a lot about what you can do to keep your machine learning system from being biased against particular subpopulations in future lectures. Another thing that could go wrong is your optimization could take too long. You could easily set up a problem for a machine learning system that could take months to run. And you will see as you're doing your assignments, you're going to be like, Geoff, come on, this takes way too long to run. Some of the assignments that you're going to need to do, you're going to probably want to press run and go leave your computer overnight and let your computer do all the processing that it needs to do to calculate all the statistics, to do all the measurements you need as part of doing professional machine learning. It may be possible in some sense to learn the model that you want, but you just don't have enough CPU resources or enough wall clock time to learn the model that you'd like to learn. And then on top of all of this is this time-changing thing where the concepts that you're trying to learn aren't universally stable. They're going to change. Who would have guessed COVID, right? Every model that every major retailer had before COVID probably isn't optimal for after COVID. And there's a lot of people churning through and trying to figure out how to adapt everything and get their systems back to working accurately. And, everybody knows that COVID's not going to be here forever, and we're going to have another phase shift as we come out of it. So machine learning, it can only learn the concepts that you have the data for, and you need to use the machine learning wisely in a system where you understand the limits of its ability to model the the processes that are going on. Then you have to deploy your machine learning, hook it up to users, run it over time, and those are all very difficult things to do. We'll talk about a little bit later in the course. We're all software professionals, and we know how to bring together a diverse set of skills, things like programming languages, algorithms, data structures, networking, et cetera, et cetera. These are all important skills that a person might have, but they aren't working systems in their own right. In order to have a working system, you have to bring these together, and you have to include management and program management and planning and operations and a whole bunch of other things. And generally, the collection of skills that organize these base skills and turn them into working systems is known as software engineering, or that's the field of study. In machine learning and AI and sort of data-based, not databases, but data-based programs and systems, you have to add a whole new set of base skills like statistics, data science, machine learning, some domain-specific stuff like computer vision or natural language processing. But then you still have to use the skills from the previous, the traditional software skills, and you have to bring all of this together and produce working systems. And one way you could maybe call this is machine learning engineering, although that's tending to be used for the act of building the systems that do the machine learning. You might also call this machine learning architecture. So, there you go, overview of machine learning. It's a lot to cover. I know my brain's spinning and I already know this stuff, right? I just had to say things that I already know. You guys are all trying to absorb this, and I can imagine it's a little bit overwhelming, but don't worry. We're going to go through all of these things again and again and again. You're going to see these words over and over, and these types of conversations will become, I hope, easy to you, start to become second nature, and you'll be able to communicate and work with machine learning professionals when you're done with this course. Let's do a quick summary of what we learned today. We went through the reasons and some of the successes for machine learning. You might want to use machine learning if you have big problems, open-ended problems, time-changing problems, intrinsically hard problems like human-level perception, and there's lots of things in the world that are benefiting from machine learning, and you use them all the time. Then we talked a little bit about the types of learning, and those are supervised, where you have features and labels. They're unsupervised, where you have features without labels. Semi-supervised, which is common in practice, where you have some of your data is labeled and much of it isn't. And then reinforcement learning, where an agent gets to interact with an environment to essentially create its own data as it goes. In supervised learning, you have training data, which is X and F of X. Remember, X is a synonym for features, and F of X is a synonym for Y or a synonym for labels. And the goal is to learn an F of X that matches the training data well, but more than that, that generalizes from the training data to the future data that you're going to see. And every machine learning algorithm, particularly supervised learning algorithms, has these three components, has its model structure, the loss function that it uses when it's searching model structures, and the optimization method that it uses to try different things out. So there you go, bit of a whirlwind. We'll get into more specifics as the course goes on. Thanks.